Welcome! In this differential equations tutorial, we're going to look at some physics problems that give rise to a differential equation, and then we're going to solve those differential equations. So some of these are spring mass differential equations, where we have acceleration, we have resistance due to something like air, and we have Hooke's law. Then we're going to look at some circuit problems. That might be it. Okay, so let's get started with the spring mass problems. So we have something like a ceiling, and from that is hanging a spring and a mass. Okay, so something like this. Now, in the presence of gravity, there's a natural equilibrium, say here. Okay, and so without an external force acting on this, what we would have is the equation mass times acceleration. So that's mass times the second derivative of x with respect to t. Then we would have the force due to air resistance. So some constant, say alpha times the velocity, x dash as a function of t. And then we would have the force due to Hooke's law, k times x as a function of t. Now, in the absence of an external force, the sum of these would add up to 0, because the three forces should be in equilibrium. And so let's write this in the absence of external force. Okay, now with an external force, well, then it looks like this is equal to f of t. Okay, and so this is the main equation that we'll be dealing with when it comes to problems like in my problem set here. So these problems mostly come from Schwamm's outline series, if not all of them. All right, so let's get started on the first one. So in the first one, we have a mass of 0.4 grams. So let's draw a picture while we're looking at this. So this is question 1. We have a spring carrying a mass equal to 0.4 grams, which is, if we convert this to kilograms, and we should, so that everything is in SI units, 0.0004 kilograms. So just divided that number by 1,000, because there are 1,000 grams in a kilogram. All right, so now that we have that, let's keep reading. It's hung on a spring and it stretches 3 centimeters from its natural length. Okay, so if this here, where I've put the dotted lines above, is the natural length in the absence of gravity, then this is 3 centimeters, which is 0.03 meters. Again, in SI units. Okay, we've got to find the spring constant. So what we have then is Hooke's law, which is F is equal to the spring constant K times that displacement. Okay, now this is equal to mass times gravity in this case. And so we can get our spring constant K by dividing by that X. And so what we're going to get is 0.0004 kilograms times 9.8 meters per second squared divided by 0.03 meters. All right, and so when you do this calculation, what you're going to get is 0.1306 recurring kilograms per second squared, or 0.1306 recurring Newton meter. Okay, question 2. So in question 2, let's draw a ceiling and a spring suspended from that ceiling. And the mass of this spring is 0.02 kilograms. Okay, so let's pause my animation there of a spring compressing. Now we're given the spring constant in dynes per centimeter. So K is equal to 2880 dynes per centimeter. But you might be wondering, what is a dyne? Okay, well, 1 dyne is 10 to the power of minus 5 newtons. 1 centimeter is 10 to the power of minus 2 meters, 0.01 meters. So we need to convert dynes into newtons per meter. So then we have 2.88 times 10 to the power of 3 dynes. But 1 dyne is 10 to the minus 5 newtons. And then 1 centimeter is 10 to the minus 2 meters. Okay, great. So now we can simplify this. So this is 2.88 times 10 to the power of 3 minus 5 plus 2, because we can bring this up to the numerator. And when we do that, we change the sign of the exponent. Now the sum of those exponents is 0. We have 10 to the 0 there. So this is just 2.88 newtons per meter, which is our spring constant. Okay, now we have another thing to write down. M equals 0.02 kilograms. What else? Well, we have alpha, the coefficient of resistance to motion, is 0. We have F of T, the external force, is 0. Okay, and we also have initial values. So X of 0 in this question is equal to 0.03 meters, because we're told that it's set in motion by stretching the spring 3 centimeters from its equilibrium position. So equilibrium position being there. This is the positive direction of the x-axis. And then X dash of 0 is 10 centimeters per second downwards. So in the positive direction. So that's 0.1 meters per second. Okay, now with this information, let's write down our differential equation. So we have mass 0.02 kilograms times acceleration x double dash, and then we have plus 0 times x dash, because alpha is 0, and then we have spring constant times x, so plus 2.88 x, and this is 0. Okay, now we want to divide throughout by 0.02, and when we do that, we get x double dash plus 288 divided by 0.02, which is 144 times x. And so next we want to write down our characteristic equation. So we get lambda squared plus 144 equals 0. So now we take that 144 over to the right-hand side, which gives us lambda squared is minus 144. And we take square roots. Now 144 is a perfect square, so it's minus 12 squared on the right-hand side. So taking square roots now, we've got lambda equals plus or minus the square root of minus 12 squared, which is plus or minus 12i, where I is the square root of minus 1. Now this has 0 real part, and the absolute value of the imaginary part is 12. So we have x of t is equal to e to the power of 0t. So e to the power of 0 is 1. And then we have a cos of 12t plus b sine of 12t. Okay, so next let's use these two initial values to find the a and the b. So x of 0 is a cos of 0 plus b sine of 0. And this is, since cos of 0 is 1 and sine of 0 is 0, this is just a, but the left-hand side is 0.03. So this gives us that a is 0.03. All right, now for the for the x dash of 0 is 0.1 meters per second, we need to differentiate this equation. So let's differentiate this. X dash of t is, using the chain rule, the derivative of cos is minus sine, but we also have to differentiate 12t with respect to t and put that in front. So using the chain rule, we have minus 12a sine of 12t, and then the derivative of sine of 12t is 12 cos of 12t. So we have plus 12b cos of 12t. Okay, let's substitute t equals 0 in here. So when we do that, we have 0.1 equal to minus 12a sine of 0 plus 12b cos of 0. Sine of 0 is 0, cos of 0 is 1. So this gives us 12b is equal to 0.1, which is 1/10. And so, dividing throughout by 12, we have b equals 1 over 12 times 10, which is 120. Right, so with this, we now have a and b. So let's sub that in and express our solution to this differential equation. And so we've got x of t is equal to 0.03 is 3 over 100 cos of 12t plus b, which is 1 over 120 sine of 12t. And there we have it. Okay, let's move on to RCL circuits. So in an RCL circuit, we have resistance, we have current, so R times I, plus inductance L times the rate of change of the current with respect to T, plus 1 on C, the capacitance, times Q of T is equal to the force applied by the voltage, I believe. Okay, and so there's our equation for this. Now I is a rate of change, dq on dt, of the charge. Okay, and so with this in mind, if we differentiate this again, di on dt is equal to second derivative with respect to t of the charge q. Okay, and so we want to take these two, put them in here, and write an equation involving the second derivative of q, the charge. All right, so now we first want to differentiate this throughout. Do we know? Because di on dt is the second derivative. So we're just replacing di on dt here with d2q on dt squared. So then we have L q double dash of t plus Ri, but I is q dash of t. And then over here we have plus 1 on C Q of T equals E of T. Okay, so now let's divide throughout by L. So we have Q double dash plus R on L, Q dash plus 1 on LC, Q of T is equal to E of T over L. Okay, and so this will be the main equation that we'll work with here. So in question 4, we have an RCL circuit with R equals 6 ohms. We have C is 0.02 farads. L is 0.1 henries. We have E of T is 6 volts. And we have no initial charge, so Q of 0 is 0, Q dash of 0, no initial current, so Q dash of 0 is 0. Okay, so now let's use this differential equation. So this gives us Q double dash of T plus 6 over L, so 6 over 0.1 times Q dash of T, and then we have 1 over L times C, so L is 1/10, and C we can write as 2 over 100 or 1 over 50. And this is times Q of T. And then on the right-hand side, we have E of T over L. So that's 6 over 0.1. And now we just need to simplify this equation and solve it. Okay, so moving on, Q double dash, 6 over 0.1 is 60. Q dash. On the denominator here, we have 1/10 times 1/50 is 1 over 500, but inverting this gives us 500 times Q, and then on the right-hand side, we have 6 over 0.1 is 60. Okay, so there's our differential equation. Now let's also remind ourselves that we have these initial values. There. Okay, so let's begin to solve this. So we've got something on the right-hand side, not just 0. So this is not homogeneous. It's second-order linear, though. And so the general solution is the homogeneous solution, or the solution to when we have 0 on the right-hand side, plus a particular solution. Okay, so let's go ahead and write down our characteristic equation for the homogeneous solution. So lambda squared plus 60 lambda plus 500 equals 0. Now we can factorize this we can factorize this quadratic equation and write lambda plus 10 times lambda plus 50, because 500 is 10 times 50 and 10 plus 50 is 60. And so this gives us lambda 1 is minus 10 and lambda 2 is minus 50. Okay, so using these to form Q homogeneous, we have A e to the power of minus 10 t plus B e to the power of minus 50 t. Now we need Q particular. So we'll guess QP for particular equals just a constant, because we just have a number on the right-hand side. So let's call that lowercase a. Okay, and then we want to differentiate. So QP dash is 0, QP double dash is 0, and sub these into our differential equation up here. So then we have 0 plus 0 plus 500 times A is equal to 60. So dividing throughout by 500, we have A is equal to 60 over 500, which is 6 over 50, or 12 over 100. And I write it this way because that's clearly 0.12. All right, so now we can write our solution to this, our general solution, q as a function of t is equal to 0.12 plus a e to the minus 10t plus b e to the minus 50t. Okay, so now that we have our general solution, let's use our two initial values up here to find a and b. So q of 0 is 0.12 plus a e to the 0 plus b e to the 0. And so that is a plus b plus 0.12, and this is equal to 0. Okay, so next we need to differentiate this line to use our second initial value. So q dash of t is equal to 0 minus 10a e to the minus 10t minus 50b e to the minus 50t. And this, when we sub in t as 0, we'll get 0. So now q dash of 0 is equal to minus 10a e to the 0 minus 50b e to the 0. And so we have minus 10a minus 50b is equal to 0. All right, so let's now get a new page, collect these two linear equations we have in a and b, and solve those for a and for b. So the first one we found was this. So a plus b is equal to minus 12 over 100, or minus 0.12. And then this one here says that a is equal to 50 over 10, or minus 50 over 10, which is minus 5b. Okay, and so now with this, we can substitute in minus 5b for that a up in the first equation, which gives us minus 5b plus b is equal to minus 12 over 100. And so on the left-hand side, we have minus 4b. And then on the right-hand side, we have a negative number. So if we're dividing that minus 12 by 4, then we get b is equal to minus 12 over 4 all over 100, which is plus 3 over 100. Okay, so there's b. Now we need to use this to get a. So let's just sub that into the second equation and write a is equal to minus 15 over 100. So minus 5 times 3 over 100. Okay, great. So let's use the two of these, sub that into our q of t. So q of t then is equal to 0.12 plus minus 15 over 100 e to the power of minus 10t plus 3 over 100 e to the power of minus 50t. Okay, and we can even tidy this up because that 12 over 100 there has a 1 over 100 in it. So we can write all of this as 1 over 100, 12 minus 15 e to the minus 10t plus 3 e to the minus 50t. Okay, question number 6. So let's seek out the data here. We have an RCL circuit with resistance R equal to 16 ohms. Capacitor C is 0.02 farads. And inductance L, 2 henries. E of t is 100 sine of 3t. Okay, now that should be enough. to find our differential equation. So q double dash plus 16 over 2 q dash plus 1 over LC, so 2 times 0.02. So that's 2 times 2 over 100 times Q, and this is equal to 100 sine of 3t. All right, now we do have some initial values as well. No initial current and no initial charge, so that's Q of 0 is 0 and Q dash of 0 is 0. Okay, let's simplify our differential equation. So we have Q double dash plus 8 Q dash. Now this is 4 over 100, but if we were invert this, we have 100 over 4, which is 25. So equal to 100 sine of 3t. All right, so let's see. We want to factorize this, but it doesn't look so easy. So let's just use the quadratic formula in our characteristic equation to find Q homogeneous. Okay, so there's our characteristic equation, and so we write lambda is minus 8 plus or minus the square root of b squared is 64 minus 4 times 1 times 25, and that's all over 2 times 1. Okay, let's simplify this. So 64 minus 100 is minus 36. And so that's all over 2. Now the square root of 36 is 6. So we have minus 8 plus or minus 6i over 2, which gives us lambda is minus 4 plus or minus 3i. Okay, so now we can write down our homogeneous solution. So Q homogeneous is e to the power of the real part times t, so e to the minus 4t, then in brackets a cos of 3t plus b sine of 3t. Okay, so now for the particular part, and I think we should get another page for this. So guess QP for particular equals lowercase a cos of 3t plus lowercase b sine of 3t. And we want to differentiate this 2 times and sub into our differential equation so we can find out what the a, lowercase a, and the lowercase b are. Okay, so QP dash is minus 3a sine of 3t, and differentiating b sine of 3t, we have plus 3b cos of 3t. Now differentiating this again, we have minus 9a cos of 3t minus 9b sine of 3t. Okay, and we want to take these 3 and sub those back into this differential equation up here. Okay, so taking those, subbing them in. Now it's going to get a little bit of messy, so you want to save some space to write all of this. Okay, so let's start with QP double dash. So we'll put the cos in front, so minus 9a cos of 3t minus 9b sine of 3t. And then we have 8 times qp dash. So that's 8 times minus 3 is minus 24. But let's go with the cos first. That's plus 24b cos of 3t. Okay, then minus 24 a sine of 3t. Okay, next we have plus 25 of the QPs. So plus 25 a cos of 3t plus 25 b sine of 3t. Okay, so all of this, these 6 terms add up to 100 sine of 3t. Okay, so let's express this in terms of cos and sine. So the parts with the cos next to them, we have 25 minus 9 is 16a plus 24b cos of 3t. And then the parts with the sine, 25 minus 9 is 16. So we have minus 24a plus 16b sine of 3t equals 100 sine of 3t. Okay, so comparing the coefficients of cos and sine, this gives us 2 equations in lowercase a and lowercase b. So we get then 16a plus 24b equals 0 because there are no causes on the right-hand side there. And then we have minus 24a plus 16b is equal to 100. Okay, so some simultaneous equations to solve in lowercase a and lowercase b. So what we can do here, take the first one and solve for a. And so we get a is equal to minus 24 over 16 times b. Okay, and so simplifying this, we can write this because 24 is 8 times 3, so we can write minus 3 over 2b. And then take this and sub it into the second equation. So then we'll get minus 24 times minus 3 over 2b plus 16b is 100. Okay, so minus 24 over minus 2 is 12, and 12 times 3 is 36. So 36b plus 16b is 100. 36 plus 16 is 52. So b is 100 over 52. Okay, and then we can get a directly from this. Let's simplify this first. So 52 is, isn't that 13 times 4? So we have 25 over 13 for b. Okay, and so that gives us a is equal to minus 3 times 25 is minus 75 over 2 times 13 is 26. Okay, so great. Now let's move on to another page and rewrite this. We found that lowercase a is minus 75 over 26, and lowercase b is, let's write this 50 over 26. Okay, now having multiplied that by top and bottom by 2. Okay, so now with that, we can write QP is equal to, in brackets, 1 over 26 times minus 75 cos of 3t plus 50 sine of 3t. Okay, and then recall that we found, where did we put this? Here we found Q homogeneous, so our general solution, Q of t, is equal to e to the minus 4t, a cos of 3t, plus b sine of 3t, and then plus this particular solution, sine of 3t. Okay, so there is our general solution. Now, remember we had Q of 0 is 0. So when we sub in and replace t with 0 here, we have 0 is equal to e to the 0 is 1. So a cos of 0 is 1. Sine of 0 is 0. So this part will just give us a when we sub in t is 0. And over here, we'll get minus 75 over 26 because sine of 0 is 0 and cos of 0 is 1. All right, so this gives us uppercase A is 75 over 26. Now, we need to differentiate this line so that we can use Q dash of 0 is 0. So Q dash of t is, well, this one's a little bit tricky, isn't it? For this, we need to use the product rule. Okay, well, I'll try to do this here without making a mistake. Okay, so we have A outside of well, you know what? This is probably easier if I just use the product rule with this u and this v. So let's try that. So A cos of 3t plus B sine of 3t. And then we have times minus 4 e to the minus 4t. And then we swap these when we differentiate. So next we're going to differentiate this and multiply by e to the minus 4t. So we have plus e to the minus 4t times minus 3a sine of 3t plus b cos of 3t. And then we differentiate this one. Okay, so plus 1 over 26 in brackets 75 times 3. I think that's 225, isn't it? 225 sine of 3t. Okay, 50 times 3 is 150, so plus 150 cos of 3t. So I think we've correctly got the derivative now. So now what we need to do is sub in t is 0 to this. So using our initial value, q dash of 0 is 0. We have then 0 is equal to a times minus 4. And then over here we have plus b for this piece. And then here we're going to have plus 150 over 26. Okay, so this is equal to 0. And so rearranging this equation, we have b is equal to 4a minus 150 over 26. And so multiplying 75 by 4, we have 150 times 2 is 300. So 300 over 26. So 300 minus 150 all over 26. And so that gives us B is equal to 150 over 26. And A is equal to 75 over 26. All right, so now let's go back to this line up here, and sub in our uppercase A and our uppercase B. And so that gives us Q of T equals 75 over 26 cos of 3T plus 150 over 26 sine of 3T in brackets all times e to the minus 4t, and then plus 1 over 26 minus 75 cos of 3t plus 50 sine of 3t. Okay, so as I start to do question 7, I see that the question 6 asks us for an expression for the current, and so we need to differentiate this line to get the current. So I of t is equal to Q dash of t. And so just to make this quick, I've just written this in Mathematica, and so then I'll just differentiate this and write that down for you. Okay, so then the derivative is, well, let's just take this and factorize this. So I'll factor out the first part of it here to make this a little bit more tidy. Okay, then. So we have 75 over 26 e to the minus 4t in brackets 2 cos 3t minus 11 sine of 3t. And then we have the rest of it plus 1 on 26, 150 cos of 3t plus 225 sine of 3t. Now, what is the steady state current expressed in plus or minus a cos omega t minus phi? All right, so the steady state is the limit as t goes to infinite of I of t. All right, so where does this end up eventually? Okay, and so if we apply that limit to e to the minus 4t, we get 0 for this part. So the steady state part of this, or steady state current, is 1 on 26 times this, but let's just expand this and say 150 over 26 cos of 3t, and then we have 225 over 26 sine of 3t. And so now we want to express this as plus or minus a cos of omega t minus phi. Okay, and so let's just take a note here that C1 cos of omega t plus C2 sine of omega t is equal to the sine of C1 in brackets square root of C1 squared plus C2 squared cos of omega t minus phi, where phi is equal to the inverse tangent, arctan, of C2 over C1. Okay, and so we're using an angle addition formula for the cosine. So let's have a look at this. Omega, in our case, is 3. C1 and C2 are both positive, so the sine of C1 is 1. And so we have then that the limit as t goes to infinite of I of t is equal to the square root of C1 squared, which is 150 squared. Now I'm factoring out that denominator because it's common in both. So let's put that out the front, 1 over 26. Then we have plus 225 squared. And then we have cos of 3t minus phi, where phi is equal to the inverse tangent of the ratio C1 over C2. Now that would be 225 over 150. And I'll leave it there. Thanks.